Welcome to all those who have tuned in to this session. Today we are going to do the last of the 8 sessions that have been allocated for the junior learners under the banner of the South African Maths Foundation, and it is entitled, as we saw in section 7 or session 7, this will also be on geometry. So we are continuing the geometry lessons that we began in the last session. In the last session, if I can recall, we said something about triangles, congruence of triangles, parallel lines, isosceles triangles, equilateral triangles. So there were many pieces of information about triangles. Today, we will go advance to some other results, maybe on triangles, maybe 1 or 2 things on parallelograms, and also we'll deal with some problems involving circles. All right, so without much further ado, we will go straight to the very first problem. And I'll share the screen with you. It is this problem. But before we do this, tackle this problem, I need to say a few things. While triangles are 3-sided figures, a plane figure which has got 3 straight lines as its boundary, quadrilaterals are 4-sided figures. And there are many special types of quadrilaterals, as we can see in this diagram. So let's see what the different types of quadrilaterals we have. Here, the first quadrilateral is random, just a 4-sided figure, no conditions attached. Now, if you take one pair of opposite sides, and if such a pair is parallel, like in this figure, you'll see one pair of opposite sides is parallel, then we call it a trapezium. So a trapezium is a quadrilateral with one pair of opposite sides parallel. I want you to know that these are the definitions. They are the actual meanings of these words, and we say nothing more than what we will say here. The other facts and properties of these figures will come out as theorems later on, but I'm telling you exactly what these things mean. And the area of a trapezium is, if you recall, it's half the sum of the parallel sides times the height. The height is the perpendicular height between them, right? So if you take the distance between these 2 parallel lines, that is called the height. Right. Now, what is a parallelogram? A parallelogram is, again, a quadrilateral, but in this case, you have not just one pair of opposite sides parallel, but both pairs. This pair, opposite sides, they are parallel, and these pair, another pair of opposite sides are parallel. So such a figure is called a parallelogram. As the name suggests, parallelogram, the opposite sides are parallel. Now, if you take a parallelogram, which you already know, with the opposite sides are parallel, and if it happens that one of the angles is 90 degrees, right, as you can see here, then this parallelogram becomes a rectangle. Right? So a rectangle is a parallelogram with one of the angles equal to 90 degrees. Right? Or if you start with a parallelogram and you say that the 2 sides next to each other, which you call adjacent sides, the 2 adjacent sides are equal, like in this picture here, the adjacent sides are equal, then the parallelogram is called a rhombus. Right? Now, I will say later on that in any parallelogram, the opposite sides, we know them to be parallel, but it can also be shown that they are equal. And that is not in the definition, but it is a theorem in geometry which says that the opposite sides of a parallelogram are equal. Right? So in this case here, this is already a parallelogram. A rhombus is a special parallelogram. So the opposite sides are equal. This is equal to that, and that is equal to that. So you see that a rhombus has got all the four sides equal, right? All of them are equal. Now, if you take a rhombus where all the sides are equal, right, and one of the angles is 90 degrees as well, then you get a square. Okay? So a square, if you want, you can look at it in another way. A square is a rectangle, right, which is also a rhombus. In other words, a rectangle, but the adjacent sides are equal. So it's called a square. It's a very popular figure. It's one of the best quadrilaterals you can get because all the four sides are equal. And it also happens that all four angles are equal, right? So it is what you call a regular quadrilateral. All the sides are equal and all the angles are equal. And then the last one that we will talk about is a kite. A kite is not a parallelogram. Right? It's none of the other ones, but it has a special property that two pairs of adjacent sides are equal. This pair of adjacent sides, adjacent means next to each other, and the other pair are also equal. So whenever you have that situation, you have what you call a kite. These quadrilaterals, namely a trapezium, a parallelogram, a rectangle, a rhombus, a square, a kite, all these quadrilaterals have special properties, right, which are not in the definitions which we spoke about. These were the definitions, but they can be proved as theorems, right? So that's what geometry is all about. You are given a few pieces of information and you can prove some other properties and some other facts arising from those pieces of information. So let's have a look at the very first one. So if you start with a parallelogram like this, I told you earlier on that you can prove that the opposite sides. So remember, the parallelogram is opposite sides are parallel. These are parallel. That's what's given. But you can prove that the opposite sides are equal over and above being parallel. Now, how do you do that? I'm going to do that very quickly. What you do is, because they are parallel, you know that alternate angles are equal. So if this is x, so is x. And if this is y, you have a z here, like this. So this is y. And then if you look at these two triangles, right? Oh, by the way, if you join these, we have to join a diagonal. And once you join a diagonal, to prove they're equal, you have to do this as a construction, all right? And then you see that these angles are equal. Now, these two triangles, a diagonal breaks up a quadrilateral into two triangles. These two triangles are now congruent. You can see quickly. You got the side is shared between the two, it's common, and you got the two angles and a side. So these two triangles are congruent, which means that these two triangles are equal in every respect. All six properties of this triangle are equal to the six properties of the other triangle. So in particular, you will have that the side here, which is opposite y, will have to be equal to the side in this triangle, which is opposite y, and that's the one. And these sides turn out to be the opposite sides of the original parallelogram. And likewise, this side here is opposite x in this triangle, and it will be equal to the side in the other triangle, which is opposite x. So you have the both opposite sides, both pairs of opposite sides are equal. Right? Now, it turns out, okay, we'll come back to that. So this is an important property of a parallelogram. The opposite sides of a parallelogram are equal. Okay. Now, if you join the other diagonal, the two diagonals, if you join the other diagonal, then what you get is another very interesting thing, that each of these diagonals, they cut the other diagonal. But interestingly, they will cut them, when they cut them in halves. In other words, this piece here, which is cut by this diagonal, right? These two parts are equal. And likewise, these two parts are also equal. So each diagonal, we say, bisects the other diagonal. Or in another way of saying it is that the diagonals of a parallelogram bisect each other. So that's another very important property of a parallelogram. Okay, now all these, the rectangle, the rhombus, and the square, they are all parallelograms. So because they are parallelograms, they will also have exactly the same properties. We said that these two are equal, those opposite sides. Here too, as we said earlier on, the opposite sides are equal. This equals this, and this equals this. So in a rhombus, all the four sides are equal, right? And of course, a square is a special kind of a rhombus. So all the sides are equal in a square as well, right? So that's an interesting thing. Now, in a rectangle, because these lines are parallel, right? You know that co-interior angles add up to 180 degrees. So if one angle is 90, this will also be 90. And these two angles are co-interior. So if this is 90, that is 90, and so on. So if you know that one angle of a parallelogram is 90 degrees, you can conclude that all the angles are 90 degrees. And this is usually the definition of a rectangle, a quadrilateral with all angles equal to 90 degrees, right? Another useful thing about a rectangle, we already know that the diagonals bisect each other, but another very important property of a rectangle is that the diagonals are not only bisect each other, but they are equal in length. You can't say that for a general parallelogram. You can't say that in any parallelogram, the diagonals are equal. You can see one is a long one, another one is a short one in a random parallelogram. But in a rectangle, the diagonals are actually equal. And since we know that the diagonals they bisect each other as well, then you have this interesting thing that these are equal, but this is exactly equal to that. So the halves will also be equal. Right? So all these four lines are equal in a rectangle. You can put the same symbol, but here you can't put the same symbol because you don't know whether they are equal. So a rectangle has got this property. And we know that the square is a rectangle, so you also have the same property of a square, that the diagonals of a square are also equal because it is a special rectangle. And also we have, a square, diagonals are equal. And as we saw before, well, all those four pieces will then be equal. So we can make these equal. So that's a nice thing about a square. All right. Now, if you look at a parallelogram where the adjacent sides are equal, like those two, what can we say? Well, if you take a single diagonal, in this case here, take a diagonal like this. Right? We know that it's a parallelogram, so the opposite sides are parallel. So if I call this x, this will also be x. But now this triangle here, right? The diagonal divides into two triangles. This triangle, the two adjacent sides are equal here. So this is an isosceles triangle. So it turns out that a diagonal of a rhombus, it bisects the opposite angles. See? The same thing with the other one. All right. And the other interesting thing about a a rhombus is that the diagonals, they're perpendicular to each other, which is a very powerful statement. And that's in a rhombus. You don't have that here. You can say they're not perpendicular in general, but in a rhombus, the diagonals are perpendicular to each other. So all these angles are 90 degrees, right? So that's another important property of a rhombus. So since a square is a rhombus, it means, it's a parallelogram with all the sides equal. So even here, all those angles, the diagonals are perpendicular to each other. So in a square, you have that all these four angles are 90 degrees. Okay. But the other nice thing about a square is that since a square is a rhombus, that means each diagonal bisects the opposite angles. Now this is 90 degrees, so therefore these angles will be 45 degrees. That's in a square, because the angle in the corner of a square is 90 degrees. You can't say the same in a rhombus. And in a rhombus, the diagonals bisect the opposite angle. So all these angles are 45 degrees. Very important property of a square, that all these 8 angles are equal. They're all equal to 45 degrees. Okay, so that gives you a lot of properties of a square. Right? And now also, which we're not going to go into any detail, but an important, okay, before we go on to that, the kite, the only important thing about a kite is that the diagonals, one diagonal bisects the other. You don't have each diagonal bisecting the other one. You have one diagonal, one of the diagonals. That's the diagonal which joins the two vertices of the isosceles triangle. Right? These two isosceles triangles on both sides. Right? If you join the vertices of the isosceles triangle, that is perpendicular to the other diagonal. Not only that, it actually bisects it. So you have this kind of thing in a kite. These are equal, and these angles are 90 degrees. Okay. Next, we go on to a rather important question. And the question is, if you are given a quadrilateral, can you prove that that quadrilateral is a parallelogram? In other words, under what conditions would a quadrilateral be a parallelogram? You're not given it's a parallelogram. You're not told that its opposite sides are parallel. But even without that information, you may be given some other piece of information which will make you conclude that it is a parallelogram. And the answer is there are 3 different ways in which you can conclude that a given quadrilateral is a parallelogram, right? And these 3 are encapsulated within this red boundary line here. You can see the first one is, if you know that this quadrilateral, the diagonals bisect each other, you know that, you don't know anything else, right? Then you can conclude that the opposite sides are parallel. So you're not given that. And once you know that the opposite sides are parallel, then it is a parallelogram, because that is exactly what a parallelogram is. It's a quadrilateral with the opposite sides parallel. So you want to show if a good quadrilateral is a parallelogram, you have to show that the opposite sides are parallel, right? So if you look at this, you can try it out. You can get congruency, and therefore from congruency you can get alternative angles equal, and therefore you can show those signs of parallel. I'm not going to do that. That's a theorem in geometry. The second important condition under which a quadrilateral is a parallelogram is when you know that the opposite sides are equal. Suppose you know that that equals that, and that equals that, and you're not given that it's a parallelogram. You're not given that the opposite sides are parallel. Then you can conclude that this quadrilateral is a parallelogram. given only those are equal, you can conclude that the quadrilateral is a parallelogram. And I will tell you very quickly in half a minute the way to do that. How do you conclude that this is a parallelogram? You join a diagonal, you will see that these two triangles are congruent because the three sides of this triangle are equal to three sides of the other. And once you know that they are congruent, then it turns out that they will have the same, all the properties are equal. In particular, all the angles are equal. This angle here in this triangle, which is opposite double stroke, is equal to the angle opposite double stroke in this angle. Then you say, but wait a minute, these angles are alternate angles. And if alternate angles are equal, then these two lines will have to be parallel. And likewise, you can show that those two lines are parallel, and the opposite sides are parallel, therefore it's a parallelogram. Right? And in the same way, this is another very important result. Namely, if you've got a quadrilateral, you don't know that the opposite sides are parallel, but you know that one pair of opposite sides are parallel, like in the trapezium, only one pair. But you also know that these sides which are parallel are also equal in length. So if you've got just one pair, which is parallel and equal to each other, then you can conclude that this quadrilateral is a parallelogram. I know I've told you quite a few things now. It's quite a mouthful, but please pause and study everything that I've said so far and make sure you understand all these results. Remember them. It's very important to remember them because these are theorems in geometry, and you will be called upon very often to apply these theorems to various problems. So you must know what the theorems are, what is given, and what conclusions you can come to. See, that is what we had. So far we said if you are given that opposite sides are parallel, you can make various conclusions. If you are given that the diagonals bisect each other, you can make conclusions. So depending on what you are given, you can make conclusions. And that's what theorems are all about. So now we go to two theorems on triangles, not on quadrilaterals. And these theorems are called midpoint theorems. So what is this? What are these theorems? The first theorem says that if you've got any triangle, as you see here, and if you take the midpoints, like this point here, is the midpoint of one of the sides, and this point is the midpoint of another side. See, they are equal, so therefore these are the middle points. And if you join these midpoints, you'll get a new line. And it turns out that this new line, it is parallel to the third side. Okay, so in words, what we say, if you describe what I just said now, it says that the line joining the midpoints of two sides of a triangle is parallel to the third side. But not only that, the length of this, right? If you call these, if you name these vertices A, B, C, D, E, the length of this line here, which we've just drawn, is actually equal to a half the length of that one. Those two lines which are parallel, the small one is half the length of the big one. So that's called the midpoint theorem, a very important theorem in geometry. The line joining the midpoints of two sides of a triangle is parallel to the third side and is equal to half its length, right? And the other theorem here is, it's a converse. This time you are given only one midpoint, as you can see, only one midpoint. But from that midpoint, you draw a line parallel. In other words, you are given different things to what you are given here. You are given here that one is a midpoint, and this is a parallel. And then you can conclude from that that this line gets bisected. That's a conclusion. So if you know that this is you got a midpoint of one of the sides of a triangle, and through that midpoint you draw a line parallel to another side, then it will bisect. This parallel line will bisect the third line. So these theorems are called the midpoint theorems. And those are the only theorems I think we will do in geometry. From now onwards, we will go and work out some problems. The first problem is about areas. You are given a rectangle, B, C, D, E, and F and G are the midpoints of the sides. So in geometry, whenever you are given certain things, you will record it in your diagram. So I'm going to record in this diagram that these are the midpoints. And the way to record it is to say that is the midpoint, like that. G is a midpoint of that side, and F is also the midpoint of that side. So I'm recording that. Right. And now once I record it, this picture comes up, right, which we've just seen. You've got, in this triangle here, you've got two midpoints. So what is the question? Find the ratio, this is the ratio of the area of CEFG. So it's CEFG. In other words, the shaded part over BCDE over the whole thing. So we are required to find the area of the shaded part to the entire rectangle. So what is the ratio? Okay, so that's an interesting question. And we're going to use all the theorems that we have said so far to get the answer. All right. Now, this is a trapezium here, right? And we know the area of a trapezium. But I want to say a little bit more than that because this is the midpoint theorem comes in here. So we need to draw the height of the trapezium. But what I'm going to do is I'm going to draw the height of the triangle from B. And then what happens is from B, if I draw a perpendicular height. Right. So that line that I'm drawing, it's a construction, right? It's not there in the picture, but I've drawn a new line. It's called a construction. It is perpendicular. The line drawn from B, it's perpendicular to FG. Right. Now, from the midpoint theorem, we already know that the line that joins the midpoints, the two sides, this is parallel. So this is parallel to that. That's the conclusion of the midpoint theorem. So you know these two lines are parallel. So when I draw this perpendicular, it means that if this is 90 degrees, because they are parallel, even this is 90 degrees. Right? Okay, so so now the question is now, what is the area of the shaded part to the whole part? I'm going to give names to these areas. I'm going to call this area here X. Let's put another color here so that we don't get confused. I'm going to call this area the area of this white triangle. Let's call it X. Maybe we'll use it capital X. And the yellow part we'll call it capital Y. And this white part we'll call it capital Z. Right. Now, we've got three different areas. What can we say? Okay. Now, the area X itself is equal to this area of the white triangle is half base. And the base here is FG. And the height, let's call this height here H. This red part here, it's called it H. So X is equal to half G times H. Okay. Now, in this triangle here, you see F is the midpoint of that, and these lines are parallel. We just proved it. It comes from the midpoint theorem. And you remember the second theorem we had on the midpoint theorem is that when you got a scenario like this, one is a midpoint and this is parallel, then these are equal. They are bisected. So this part here is actually equal to this part, and that is because of the converse of the midpoint theorem, the second midpoint theorem. So if this length is H, this is also H. See? All right. So what does this mean? It means that Let's give a name to FG. Right? We'll call it FG, we'll call it Z. Z is equal to this. Sorry, I'm using the same symbol, but I'm using a small letter Z now. And we also said from the midpoint theorem that this line here, FG, is half this. That's the midpoint theorem. So if this line is Z, then this entire line here, which happens to be the diagonal of the rectangle, is twice Z. Okay? So that means now we can calculate Y. What is Y? Y is a parallelogram. The opposite sides are parallel, but only one pair of opposite sides are parallel. But we know the area of, if it's a, so it's a trapezium, because one pair of opposite sides are parallel. And we know the area of a trapezium, I said this earlier on, is half the sum of the parallel sides. This side here is Z, and the other parallel side, which is parallel to it, is 2Z. So it's half the sum of the parallel sides times the height. And what is the height between these two lines? We just saw that it is h, right? So x is equal to a half. We said fg was z. So this is zh. Okay. So now the question is, what is the yellow part? What is y? And we already got it. It's half z plus z is 2z, 3z at least, and you add 3z times h over 2. So you got a nice formula for this. It's 3z over 2 times h. That's y. And now they want to know the area of the full rectangle, right? BCDE. Now, remember, this is a diagonal for the rectangle. And we know that the diagonal, we said earlier on that a diagonal of a parallelogram, it divides the parallelogram into two congruent triangles, right? So that means these two, this triangle here, this white triangle, is congruent to the other part. So they have the same area. So the area of this entire rectangle, the area of the BCDE, is the Z here will be equal to half the area, because the diagonal bisects the area of a rectangle. So the area of this whole thing will be twice Z. Now that is twice. And remember, Z is the same as the area of X and Y put together. So we can add X and Y. What is X plus Y? It's half ZH plus 3 over 2 ZH, which makes it 2 ZH. Right, so X plus Y, you can see it's half of ZH, and here it's 3 over 2, 1.5 ZH, so it has to be 2 ZH. So this is actually equal to, twice this is 4 ZH. Right, so now we can say what this is. CEFG was Y, and the area of the whole rectangle, we saw in BCDE, is 4 ZH. But the area of the Y part is just 3 over 2, we saw. Y is 3 over 2, 3 over 2 at least, ZH, over 4, ZH. And the Z's cancel, the H cancels. 3 over 2 divided by 4 is 3 over 8. So the answer to this problem, the area of the shaded region to the whole rectangle, is 3 over 8. And we use the midpoint theorem, and we use the converse of the midpoint theorem to find the areas of the shaded region. And we also use the theorem which says that the diagonal of a parallelogram bisects the area of the parallelogram. Right? So then we can conclude that the area of this whole rectangle is twice this. twice z. Okay, so that takes care of the first problem. I've written out the proof in detail here. It's very important for you to know how to prove things. So as you saw in session 7, I'll always give you the detailed solution after I have discussed it. And here it's on the screen. And later on, you can go back to this and study it carefully. Okay, we get on to the next problem. This problem, it is given that ABCD is a square. So you can see ABCD, the 4 vertices are given, and it's given that it's a square. M is the midpoint of both BC and AP. So you're also given that M, right? We will so there's M here. It's the midpoint of AP. Okay, well, I've drawn that in. Midpoint of AP and also BC. So in other words, that is not written down here. So we will do it. We'll say these are equal. M is the midpoint of this. Okay. Now this line here was not joined. I shouldn't have had this line here at all. The question is, calculate the size of angle CBP. So what you need to calculate is this angle here, CBP. Let's trace it. CBP. So let's give an angle. Let's call it X. This should be an angle. Calculate the angle CPB. Right. So the problem is, what is this angle? And if you try to work it out as it is, you will have difficulty in actually finding this angle. And this is an example of something where you need the construction. And the construction is actually what I've mistakenly drawn here. This is actually construction. It wasn't part of this problem. Right, so the construction is join CA. That was not part of the problem, but we're going to use it to actually calculate to solve the problem. All right. So what can we see here now? What, if you look carefully, you will see that you've got CB and AP bisect each other. So what does this mean? It means, as I told you, that when you got a quadrilateral, let's complete the quadrilateral. Okay. So in this quadrilateral here, CPBA, that's a quadrilateral. We see that the diagonals of this quadrilateral, these are the two diagonals, they bisect each other. And one of the things I told you is that when you got a quadrilateral where the diagonals bisect each other, you can conclude that it is a parallelogram, right? You can conclude that the opposite sides are parallel. So in this case here, I can actually conclude that this line is parallel to this line, right? Now, once you've got those two lines are parallel, then if you look at this X here, X actually turns out to be equal to some other angle in this picture, because you can come down this parallel line, go up this transversal and come down the other parallel line, and you've got a Z. So it's equal to, this X here will be equal to that, because these are alternate angles. You know that they are parallel because in this quadrilateral, the diagonals bisect each other. So they are parallel. That's a theorem, geometry. But now if you look at this X here, you've got a square. And if you remember, I told you in a square, when you take the diagonals bisect the opposite angle. So this angle is the same as that. The whole thing is 90 degrees. So X is equal to 45 degrees. All these angles in a square, if you draw the two diagonals, those 8 angles are always equal to, each of them equals 45 degrees. So that was the problem, to find X, and we have just solved it. Before we proceed to the next problem, I want to say something about polygons. We have spoken about polygons in the last session, but quickly I need to recall some of the things. I will assume that you already know about polygons. But just to recap, a polygon has a number of sides and a number of angles. The number of angles is equal to the number of sides. In this picture here, you will see it's got 7 angles. So this is a 7-sided polygon. Now, no matter what polygon you take, there's a very beautiful result which says that if you add all the angles, the interior angles for polygon, that means all these interior angles like this, then you know exactly what the answer is. You don't have to know the shape of the polygon. The sum of the interior angles is always the same. It only depends on this number of sides there are. And if there are n sides, so the number of interior angles is the sum of the interior angles is n minus 2. You reduce the number of sides by 2 and multiply by 180, because we say there are n minus 2 straight angles. A straight angle is 180 degrees. All right, so in this particular case here, if you've got this polygon has got 7 sides, so when you add up all the 7 angles, you're going to get 7 minus 2 straight angles. So you have to multiply this by 180, and when you work this out, 7 minus 2 is 5, 5 times 180 is 900. So when you add all these angles, you can get 900 degrees. And another very important fact about polygons is that all the sides and, oh, wait a minute. Now this is a definition, right? It's a definition of a regular polygon. Often they speak about regular polygon. So what is a regular polygon? A regular polygon is a polygon which has all its sides and all its angles equal. All its sides and all its angles are equal. Right? One of the most, so a regular triangle, for instance, a 3-sided figure, is an equilateral triangle. All the sides and all the angles are equal. And a regular quadrilateral is just nothing else but a square. All the sides and all the angles are equal. So if you go to a regular hexagon, right, which I've drawn here, the nice thing about regular hexagon is that you can join the opposite vertices and you get a very nice picture. All these triangles, they're all equilateral. See, the 6 sides are all equal to each other, and when you join them, they all go to the same point. And the angles, the angles of a hexagon, if you add up all the 6 angles, you're going to get 6 minus 2 straight angles, right? So if you add up the whole 6 angles, you're going to get that number. But all the 6 angles are equal, which means that each of those angles is, this is 720. So all the 6 angles are equal. So which 6 numbers, equal numbers, add up to 720? It means that the interior angle, all of them are equal. So it's 720 divided by 6. And that's 120 degrees. So each interior angle of a hexagon is 60 degrees, 120 degrees. And these diagonals actually bisect those angles. So you see you got equilateral triangles, 260s and 260s. So you have all these triangles are equilateral, which tells you something very nice, because those two are equal. That is equal to this is equal to this is equal to this, because all these are equilateral. And of course, they're all equal to the sides of the triangle, because they're all equilateral, you see. So you have a very beautiful setup in a regular hexagon. Okay, so that takes me now to the next problem. It says the diagram shows a square inside a regular hexagon, and you're asked to calculate this angle theta. So what have you got? You got a regular hexagon. I just spoken about this. And you got a square on one of the sides. A square is drawn. And then that corner of the square is joined to that. And you're asked to find what this angle is. Okay, so let's try to do this and see where we got to. So since it's a regular hexagon, all the sides are equal. So I can write down, let me put this in red so we can see it clearly. So this side is equal to that side. All the sides are equal because that's a regular hexagon. Okay. Now this is a square. So this side here, all the sides of a square are equal. So all those are equal. So now we see this theta that we are looking for is an angle in an isosceles triangle. See, these two are equal. So this is also theta here. Right? So we can find theta if we know what this is. So that's the question. But that's very easy to do because this angle here is 90 degrees. It's the angle of a square. And we know that the whole angle, all the interior angles we just said, are 120 degrees. In a regular hexagon, the interior angles are all 120 degrees. We just calculated it now. So this entire angle is 120 degrees. And this part here is 90. So what does it mean? It means that for this whole angle to be 120, this is 90. The question mark is 30. So this angle here is 30 to make up 120. And so once you know this angle, then the theta is easy because the three angles of a triangle add up to 180, and these two are equal. So you can say 30 plus 2 theta is 180. You have a nice equation. When you solve for it, you get theta is equal to 75 degrees. So that's the answer to question 3. Problem that we're now going to tackle is the following. If you look at the picture, you've got a square, you've got an arc here like this. So it looks as if with this center, you're drawing a circle. So this is a quarter circle. And with D as a center, you're drawing another circle. And this is another quarter circle here. So this is part of a circle. Right? So when you draw a circle, it means all the points on the circle are the same distance from D. All these points, and you join them to D, they'll all be equal because this is the center of the circle. And likewise, this is the center of the other circle. All right, so now it's also given that xy is 16 minus 8 root 2. If you look at this carefully, you'll see it's given here. There it is. xy is equal to 16 minus 8 root 2. Rather funny looking number, but whatever. Okay, now they say, what is the area of the square ABCD? Okay, to find the area of the square, well, you need to know the side of the square. So you need to calculate AB or BC or any of the 4 sides. And then once you know that, then you simply square that one, and that will be the area. So we need to know what is AB. Right. Now, if you look at AB or BA, that's the radius of this thing here. So it means BA is the same as BY. Okay? Because this, I'm drawing a circle like that. So Y, B, and AB will be the same. So to find the AB, I need to find what BY is. Okay, I already know XY. So I need to work out this piece here, because then I can say that plus this piece is the radius, or it's the side of the square, and I square that to get the area of the square. So let's give names to these symbols. Let's give a name called, let's call this A. So if you call this BX, suppose we call it A, and by symmetry, this part here will also be A. And you can see it has to be the same. So the diagonal is BD, you got 2A. So I'm gonna write down, to make life easy, I'm gonna call XY, I'm gonna call it 2B. In other words, I'm not gonna use these numbers because they are very clumsy, but I'm gonna call this quantity 2B. And just remember what B is. We can eventually calculate B. Twice B is this, so we will know what B is. All right, so we'll just hold on with that. Okay, now I need to calculate the side. Okay, now that's not going to be too difficult, because suppose we call AD, suppose we let AD be equal to X. That is what I'm looking for. Okay, so we need to calculate A and B. All right, what I'm going to do now is I'm going to join AC, right? Because I know we've got a square, you see, so we've got a lot of nice things about a square. One of the earlier on we said we got lots of beautiful properties of a square. So to do that, if you join the diagonals, then some nice things happen. Right. Now we saw that when we join the diagonals cut each other at right angles. So that's one of the first things. And these diagonals are equal because in a rectangle, the diagonals are equal. The entire diagonal BD is 2A plus 2B. Right? You got A plus 2B. That's 2A plus 2B. And so that means that just this part here, so this is also 2A plus 2B. The diagonals are equal in a square. So this part here is half because the diagonals bisect each other. So if the whole thing is 2A plus 2B, let's call this O here. Let's call it AO. AO from here to here, right, will be half of 2A plus 2B. And that is A plus B. So what we have here is the radius of the circle is A plus 2B. And from B to there is A plus 2B. So this will also be A plus 2B. Right? So because the radius of the circle is A plus 2B. And we saw that AO is A plus B, which means that I have an interesting situation here because this is A plus B, and this is also A plus B. We saw that the diagonals are equal and the diagonals bisect each other. So this will also be A plus B. And now we have in this triangle here, we've got a right angle triangle where one side is A plus B, the other is A plus B. The hypotenuse is A plus 2B. So that allows us to get an equation. See, in mathematics, we try to work towards equation, and we move toward the right angle triangle here, and we have the you can use Pythagoras to get this. So you have that a plus b, the square of this plus the square of a plus b again, there is equal to a plus 2b all squared. That's the hypothesis. I could have done it also like this. I could have said that this a plus 2b, that one, and taken this whole right angle triangle there, and we know that this whole thing is 2a plus 2b. So we could have used Pythagoras on that square plus that square is equal to this diagonal square, and we'll get to the same answer. But now we got an equation involving a and b. We don't know, we know what b is, because b, we've got some funny looking thing there. So we can substitute for b. I'm not going to do it straight away, because I want to simplify this. So when you simplify this, you get a squared plus 2ab. I'm going to go quite fast here. And this is doubled. And you're squaring a plus 2b. A plus 2b all squared is a squared plus 4ab plus. So if you take all the a squareds out, you got 2a squared. You got 1a squared here, so that's a squared. 2ab plus 2ab is 4ab. 4ab on this side cancels. And the b squareds, you got 4b squared on this side, and you got 2b squared on the other side. If you bring it to the other side, you got 2b squared. All right. So now we know what b is. So and we need to calculate a plus 2b all squared. So because that will be the area. All right, so we can substitute b is equal to it's 2 into 2b is this, so b is 8 minus 4 root 2. You're squaring that, and that is a squared, right? And you need to calculate a plus 2b all squared. All right, then you can make all these substitutions and eventually you'll get to some answer. I'm not going to go into the detail. You can simplify the calculations completely if you look at this. I should have shown you this problem. The full solution to the previous problem, number 3, I did not show that to you. So okay, let's do this first. So when you get to so you can see I've done the calculations here. I've come to a squared plus a squared is equal to 2b squared, and then you got a is equal to, you can solve for a and b and a plus 2b, as we see, and you get a very nice answer. It's 64. So you can look at this solution and it gives you a very neat solution. But from a squared equals 2b squared, you find square roots on both sides, and a will be equal to square root of 2 times b. That's what we've got here. And then when you need to substitute, you substitute for a, right? You got a is that, and you substitute for b, and you work it out, and you get a very nice answer. All right, so this is the full solution to this problem. And let me just share with you the full solution to the earlier problem. which I didn't display to you. So there it is. If you didn't, this tells you how to write the whole solution. And likewise, the solution to this problem here, right? The full solution of this is here, and you can have a look at it. At your own time. So now that takes me to problem number 5. Now let's have a look at this problem. In the figure, ABCD is a square. Right? They like asking questions on squares and equilateral triangles. So you got ABCD is a square, the large figure is a square. BM equals MC. So in other words, M is the midpoint of BC that is given. And then, so this midpoint is joined to this to get DM. And now you choose a point P on this line. And then you ask to prove the strange thing. Prove that BA equals BP if and only if AP is perpendicular to DM. Right, I just want to unpack that. So let's see what we are required to prove. We're required to prove that RTP is a shortened notation for required to prove. You want to prove that given BA equals BP, if BA equals BP, you want to conclude. We don't know that. You want to conclude that AP is perpendicular to DM. But when you say if and only if, it means that in both directions. In other words, if you are given that AP is perpendicular to DM, now that's different. Now you're given something different, but can you conclude that BA equals BP? So there are two things to prove here. If this is equal to this, implies that, and if this is perpendicular, it implies that. All right, so this looks like quite a challenging problem, and it certainly is. The main reason why it's challenging is if you try to work it out from the given information, you wouldn't be able to get anywhere, unfortunately. All right, and this is one of those problems where you have to use some other line which you must construct in order to solve the problem. So you need a construction without which you would not be able to solve the problem. Okay, and now the question is, what construction do you use? And after a lot of thought and a lot of experimentation, right, eventually a creative student will come across this construction here, which is not a very complicated construction, but it will help you to solve the problem. What you do is you take the point B and you join it to the midpoint of AD. In other words, you kind of replicate what was done here. This D was joined to the midpoint here. Now you take B and you join it to the midpoint there. So you do the same thing on the other side, as it were. And this time you know that these are equal. So that's what you did. You join B to that and stop there. And then this line here cuts this line here somewhere. Let's call this Q. Right. Now, what can we conclude? The first thing is that this is, well, by the way, I can write two strokes here because these two are equal. This is equal to that. And so therefore their halves will also be the same. So I use the same symbol. Right? So I've got a stroke here and I've got a stroke here. But we do know that this line is parallel to this because this is a square. So now, if you remember, we said if you got a line which is equal and parallel, that's what we got. this line, let's call this one here E. So ED is equal to BM, is parallel to this, and it is parallel to it. So this means that EDMB is a parallelogram. This is one of those three things which I told you, which will allow you to conclude that a quadrilateral is a parallelogram. So this is a parallelogram. In particular, it means that this line here is parallel to this. Okay. And now that's a very useful thing, because if you know that this line is parallel to this, right? It means you got in this little triangle here, you got the midpoint theorem, you see? You got this point is the midpoint of one of the sides, and you got from that point you draw a line which is parallel to the other side, and the converse of the midpoint theorem says that that line will bisect this. So from the converse of the midpoint theorem, you get that these two are equal. Right. I'm going to stop there for the moment, and I'm now going to take each of these cases and try to conclude the other. So suppose I know that BA equals BP. Can I conclude that AP is perpendicular to DM? Right. So now we are given that BA is equal to BP. Right. Suppose now you know that those two are equal. Suppose you know those two are equal. And now we are required to prove that this line here, AP, is perpendicular to DM. So we don't know this. Is this 90 degrees? There's a question mark here. We don't know. Okay, I suggest that we can prove it. Look, we are given that these are equal. We just proved that these are equal using the converse of the midpoint theorem. And this line here is common to these two triangles. So if you look at this triangle here and this triangle, those two triangles are congruent. Three sides. But the moment they are congruent, it means that these two angles are equal. But these two angles add up to 180 degrees. This is a straight line. And which two equal numbers add up to 180 degrees? It has to be 90. And so that angle there is 90. But now, if this angle is 90, we wanted to find out whether that is 90. But of course they are, because these lines are parallel. And these angles are alternate angles. So if this is 90, this will have to be 90. So the question mark is satisfied. We've just shown that this is 90. See? Let me go through this thing again. We came to this point here and we stopped. Then we said, suppose these are equal, and we compared these two triangles, we see that they are congruent, right? Three sides, and therefore these two angles are equal, and therefore they both have to be 90 degrees. And now, once they are 90 degrees, that automatically becomes 90 degrees because this line was parallel to that. The original picture was a parallelogram, right? Opposite sides are parallel. That followed from one of the theorems in geometry. Okay, so we've got this line. This allows you to conclude that. Now, the other part here now is, suppose you know that AP is perpendicular to DM. This time you are given that AP is perpendicular to DM. Okay, let me just wipe out all these red lines here. So now we are given a different thing altogether. Right. So what are we given, and what are we required to prove? We are given that AP is perpendicular to DM, and we asked to prove, does this allow you to conclude that BA equals BP? We don't know this. So again, we start here now. We start with AP is perpendicular to, now this is given. So we can write this down as given, right? We already know that these lines are parallel, which means that this angle is 90 degrees. We can conclude that this angle is 90 degrees. And now, again, you can compare these two triangles, and you will see that they are congruent. This time, you will have these angles are 90 degrees, and you got these are equal. So you got a right angle, hypotenuse, and side, and those two triangles are congruent. The moment they are congruent, you can conclude that this wasn't given. You needed to prove that these are equal. So now you can compare these two triangles, and you have two sides and included angle. Sorry, two sides and included angle. That side is common. Therefore, these two triangles are congruent, and you can conclude, therefore, that BA equals BP, and that's exactly what we wanted to do. So you can see geometry is very logical, and if you know all your theorems, and all you have to do is to just apply them at the appropriate time. I'm going to share the full solution with you so that at some time so this is the full solution, which I just said in words, but if you want to write it down, this is how you would write it down. And please learn how to write it down from one step to the other and give reasons for every step. And the reasons will always be from some earlier theorem, right? So that is what we've got. Now let me get on to the next problem. Okay, the next problem, you are given that ABCD is a rhombus. So remember, this entire picture is a rhombus. That means that all the sides are equal. And remember what we told you earlier on, that the diagonals, they are perpendicular to each other, right? Perpendicular, and they bisect each other. So these are a lot of properties of a rhombus that we should know. E is a point on BC, and if FECG is a kite, FECG, so this little thing here is a kite, they'll try to prove that ABC is equilateral. So now you are given, so we are given that FEGC is a kite, and we are required to prove, let's just write that down as given. So you can use the fact that this is a kite. We know the properties of kite. But we don't know the triangle ABC. ABC is equilateral. We don't know. So we need to prove that. Now, as I told you, this is towards the end of this, we are quite challenging problems. And this is not an easy problem. It will take you some time to solve it. And I'm going to do it for you. If you want, you can go try it out on your own before listening to the solution. But here it is. I'm going to give you the solution. Now, FEGC is a kite. It could mean that this equals this, and that equals that. Okay, but I'm not going to take that case. It actually turns out you'll never be able to get this equals this. That's impossible. And I'll show you the proof just now, and I'm not going to do it. We don't have time. But it is a kite, so therefore we can conclude that this FG is equal to that, and that line equals that line. That's a kite. All right. So where do we proceed from here? Okay, we know that the diagonals of a parallelogram bisect each other. So if this is a double stroke, that is also a double stroke there. Okay. We also know that this is 90 degrees because the diagonals of a rhombus bisect each other. Okay. So now the question is, you see, in a kite, one of the things about a kite is that the opposite angles are equal. I haven't said this earlier on. In any kite, those two angles are equal. So this is 90 degrees. Whenever you have a kite, those angles are equal. Just one pair, not those. Right? Those angles are bisected, but these other angles are equal. Okay, it's very easy to prove. So if this is 90 degrees, this is also 90 degrees. Now we have an interesting situation where this triangle here, you will see, it's congruent to this triangle because you got that equals that. These are vertically opposite angles here. These angles are equal, and those two angles are equal. So you got two angles on the side, so those triangles are congruent. So using the fact that this is a kite, I've now come to the conclusion, and using the fact that these two are equal, I've now conclude that these two triangles are congruent. Right? So what does it mean? It means that this double stroke, which is opposite curl, I'm calling this angle curl, must be equal to the angle, the side opposite curl here, which is that. So this is double stroke also. Right. Which now says something quite interesting. It means that these two are equal. See? And what happens now is that this AE is a perpendicular bisector of BC. And whenever you have a situation where we got a perpendicular bisector of a line, a very important conclusion from that is that if you got a point on if you got a perpendicular bisector, what do you mean by the perpendicular bisector? It means that the line is perpendicular to it and is also bisects it. Your conclusion is that these two are equal, because it's easy to prove that these two triangles are congruent now, right? Because this equals this is 90 degrees, these are equal, common side, and they are congruent, and therefore this equals that. The original triangle becomes isosceles. So in other words, AB equals AC. Right? AB equals AC. Right? Because you can compare these two triangles, you'll see that they are congruent. But then AB is also equal to BC, because this is a rhombus. Right? Two sides of a rhombus are equal. So in this triangle here, you got all the three sides are equal, and that exactly says that the triangle is equilateral. See, so starting from the fact that this is a kite, you can proceed in a systematic manner to prove that the original triangle is equilateral. It's a nice problem, rather challenging, but you can go over it. You can try it on your own now. And yeah, I'm going to show you the full solution. The first part of the solution is saying that you don't have that those two are equal. So you don't have to worry about it. It's rather complicated, but just assume that FG equals FE, and eventually you get the answer. Okay.